Hello, welcome to part 2 of Physics Paper 2. So I've introduced myself, but so I'll start straight away with this. Okay, so number 3. A cyclist is riding a bicycle at a steady velocity of 12 meters per second. The cyclist and bicycle have a total mass of 68 kilograms. Calculate the kinetic energy of the cyclist and bicycle. Use the equation. So I've given you the equation there. And all we have to do is substitute numbers in. So it's nice and easy, isn't it? So K is kinetic energy. So KE, you might sort of zoom into this a little bit. Let's have a bit more room. So KE equals half is just half is a number, times M. So M combined 68. Okay, times, and this is only we've got to be careful with, 12 meters per second. We need to square it. Okay, so we put that into our calculators and we get 4,900 joules. Okay, that's all we have to do there. Substitute numbers in. Okay, describe the energy transfers that happen when the cyclist uses the brakes to stop. Okay, so if it was moving, it's obviously got kinetic energy first of all. So kinetic energy, okay, we've got first. Kinetic energy is transferred to, think about it, is transferred to, brakes get hot, remember, so definitely thermal energy there, isn't it? If you brake really hard, you can actually burn your brakes out. Okay, to thermal energy. Thermal energy store, they call it, okay, in the syllabus. Or brakes and environment. It's something that goes, or surroundings, we call it. Surroundings. Okay, that's all that happens there. Surroundings. Okay, D. The cyclist starts to cycle again. The cyclist does 1,600 joules of useful work to travel 28 meters. Calculate the average force the cyclist exerts. Okay, so let's have a look. We've got energy. We've got 28. So it's actually work. Okay, it's not an obvious one. Okay, it's a little bit like the pressure in the pistons from earlier. So work is force times distance. But work is actually in joules, actually a unit of energy. So there's 1,600 joules. We're going to put F for force times 28. So rearranging 1,600 divided by 28. So what are we going to get there? We're going to get 57 newtons. Okay. Next question. So an athlete uses a training machine in a gym. The display on the machine shows the time spent on the machine and the amount of energy transferred during a training session. Figure 5 shows the displays for 2 different sessions by the same athlete. The energy 45.2 kilojoules, that's thousands of joules, time 300 seconds, or energy 37.9 kilojoules, time the same, 300 seconds. Explain what the displays show about the average power of the athlete in each of these 2 sessions. Okay, so we need to know what power is first of all. So power, okay, is equals an equation, energy transferred over time. Energy over time. Okay, so session 1, let's work it out. Okay, so 45.2, or actually, yeah, 45.2. So we'll go for, if it's 45.2 kilograms, it's 45,000. We'll do that actually, to explain it a bit better. Okay, divided by 300. That will give us 150 watts. Okay, session 2. Okay, again we've got we're doing 379, so 37,900. Also the same time. Okay, that will give us 126 watts. So what it is there is that the power is so greater power in session 1. Mr. Andres, session 1. Okay. Number 4. A student rubs a plastic comb with a dry cloth to give the comb a positive electric charge. Figure 6 shows a charged plastic comb picking up small pieces of paper. Okay, might have done that before yourselves. Okay. Explain how rubbing the comb with a dry cloth gives the comb a positive electric charge. Okay, how rubbing the comb with a dry cloth gives the comb a positive electric charge. So let's think about that. So what's actually going to be in an electron? So in an atom, you get electrons and protons. It's only the electrons that move. Okay, so the electrons are transferred. So only talk about transferred charges. Okay, only electrons transferred. Okay, so if the comb is left with a positive charge, the electrons are transferred from the comb to the cloth. So electrons, okay, are transferred to the comb from the cloth. Sorry, transferred. So let's get rid of that. So electrons are transferred to the cloth from the comb. Because, yeah, so what's happening is electrons are coming off the negative, off the comb onto the cloth, leaving the comb positive. Only electrons, so positive ions, don't move anywhere. Okay, so leaving the comb positive. Okay, so just be careful to get more marks. So I put negative electrons just to make sure we get the mark there. Okay, so that is what's happening there. Explain how the positively charged plastic comb picks up small pieces of paper. Okay, so a negative charge is induced in the paper closest to the comb. This attracts paper to the comb as opposite charges attract. Okay, simple as that. We might have done that in class. Okay, let's have a look at the next question. So which of these diagrams shows the shape and direction of the electric field around a positive point charge? Okay, so in conventional current, it always flows from positive to negative. So if it's a positive, okay, it's a positive, so it's actually the direction a positive charge would take. So it's actually A, okay, because if a positive charge was placed around another positive charge, it would repel it. Okay, it would move away from it. Okay, figure 7 shows two metal spheres. Metal sphere A is fixed to a table. Metal sphere B can be moved. Okay, so we can move this one. Metal sphere B is placed at a short distance from metal sphere A. Okay, so they're attached to an insulator. Both spheres are insulated from the table and given a negative charge. The force between the charged spheres is measured. Explain in terms of electric fields why a force is exerted on sphere B. So this again sounds harder than it actually is. So sphere A has an electric field. Okay. Sphere B is in the electric field of sphere A. It's near it. Okay, it's the first bit. Okay, and the fields overlap. So it's not like exactly like positive, negative charges. Okay, so sphere B is moved and the force between the spheres is measured at several different distances. Figure 8 is a graph on sphere B against the distance between the centre of the spheres. Okay, so it's kind of started at 6 and it goes outwards. Force on sphere B in millinewtons, distance between centres of spheres in centimetres. Describe how this force on sphere B varies with distance between the centre of the spheres. Okay, so first of all, an easier one. Okay. As the distance increases, the force decreases. It's not linear, is it? Okay, so it's non-linear. In a non-linear way. So it's not a line, it's a curve. Okay, it's actually inverse, yes, inverse square law is actually what is there. So inversely proportional, okay, will be another one, but it's an inverse square law. Like gravity. Okay, like gravity, that one. Let's look at the next question. Okay, so it's just, yeah, a bit more of, so yeah, it's not non-linear because it's a curve. Okay, a student has a bar magnet, a piece of iron the same size as a magnet, and some paper clips. Describe how the student could use these items to demonstrate temporary induced magnetism. Okay, so this is, so we've got a magnet, a piece of iron, temporary. So iron is not a permanent magnet. Okay, so how do you make it? Okay, how do you make it? So what you could do is sort of stroke the iron. You may have to, you can do this with like a fork or spoon in your kitchen. So stroke the iron, with the magnet to induce magnetism. Sorry, with the magnet to induce magnetism. Okay, so place iron near paper clips. Okay, paper clips are attracted to the iron because it's now magnetic. Okay. So we could also then over time, so wait. Okay, so wait for some time to pass. And observe less paper clips, okay, are attracted to iron, or they're attracted more weakly attracted as the iron loses its magnetism. Okay. Okay, so that will be the induced magnet. Okay, so I'm going to stop that video there, and I'll see you in the next video. So thank you for listening, and see you in the next video.